Okay, so this is an example to do connected particles. We've got two particles P and Q of masses 5 kilograms and 3 kilograms connected by a light and extensible string. P is pulled up by a horizontal force of 40 newtons along a rough horizontal plane, and the particles experience friction of 10 newtons and 6 newtons. We're going to find the acceleration of the particles, the tension in the string, and then we're going to discuss how we use those modelling assumptions. Okay, so first thing we ought to do is draw a nice diagram so we can see what's going on. So we've got two particles, P and Q. So for the sake of argument, that one could be P, that can be Q. We've got masses 5 kilograms for P, 3 kilograms for Q. They're connected by a light and extensible string. We're going to label all the forces. So we've got a force 40 newtons is pulling P, so we'll be pulling it that way. We've obviously got reaction forces for both of those. We've got the weight of these. These don't really come into our calculations, but it's worth labeling them anyway. There's tension in the string, which is going to be the same both ways. So like this tension is the force that Q's pulling back on P. Here, this is the tension, that's the force P's pulling on Q. Then we've got some friction as well. So P's got friction of 10 newtons. Q's got friction of 6 newtons. And then we've got some acceleration as well, so we'll be accelerating this direction, so I'll label that on. And then we want to actually resolve some forces, so we're going to resolve on the whole system. What that means is that the tensions will cancel each other out, so they won't be part of the calculation. So when we do that, we've got 40 newtons pulling this way, and then we've got 10 newtons against us, we've got 6 newtons against us. And as I said, the tensions cancel each other out because you've got one that'd be negative and one that'd be positive, so they don't come into it. That's equal to the mass of the whole system, which is 8 times the acceleration, F equals ma. So therefore, we're going to get 24 is equal to 8a, so therefore a is 3 meters per second squared. And again, to get tension, we want to resolve on a particle individually. So if we just resolve on P for the sake of argument, so if we just look at P, the forces we've got are 40 newtons, and we've got 10 and the tension pulling against us. And that's equal to the mass of P, which is 5, times its acceleration, which is 3. So really 30 take T is equal to 15, therefore T is 15 newtons. Now I'll just briefly discuss how we've actually used these modelling assumptions. So when we say a string is light, that means two things. One is that we don't need to worry about the mass of the string in the calculation. So like here, that 8, it's not 8 plus whatever the mass of the string is, we're just ignoring that. And the other thing it means is that the tension will be the same throughout the string. Inextensible means the acceleration of both particles will be the same, and that's why we can actually solve it in this way.